me and you can see my screen all right. If you can confirm, that will be great. Okay, thank you. So welcome back to a new lecture from Transformers for Vision. We'll be building, and before that, we'll be understanding about vision language models today. After learning about VLMs, we will also build a Nano VLM completely from scratch. In the last lecture, we looked at building a vision transformers from scratch. So some of those ideas will be very beneficial for you here in understanding the architecture. And this is, of course, under the category of multimodal LLMs, because in vision language models, you have two modalities, the modality which carries vision and the one that carries text. So now let's look at what are VLMs. Ideally, VLMs should be able to process text and image data together. So if I write a word apple, or if I show you the image of an apple, in human brain, we process both of these kind of similarly. Both of these are represented by the idea of apple inside our head. So how does that happen, right? So somehow VLMs should understand that this and the picture of an apple both mean the same thing. Now, we can think of this in multiple ways, but one of the simplest ways to think of representation is how did we represent text in a large language model? What was each token becoming in a large language model? If you can answer in the chat. Each token was represented using dash. It was basically a vector, right? So each token was converted into a mathematical multi-dimensional vector. So we can think of a similar idea here. Somehow convert apple into a vector of n dimensions, and somehow convert this image of the apple also into a vector of the same dimension, same number of dimensions, and then figure out how to make these two representations close to each other or similar to each other. So if you look at this image, it very nicely captures this whole idea. So this is the vector of the text dog. This is the vector of the image dog. They should be very similar. Ideally, they should be close to each other because this is a semantic space, multi-dimensional semantic space. And each area of this space, when you are pointing a vector to that area, it has a specific meaning. So in general, you can think of vectors corresponding to animals pointing to the semantic space for animals, vectors corresponding to fruits like apple, orange pointing to another direction in the space. But what we want is, we want the vector embedding of the text of dog and image of the dog to be same. And this we have discussed many times in this course. How do we quantify similarity between two vectors if the dimensionality is the same? We take cosine similarity, correct? We can take the dot product and construct a cosine similarity. So if these two were unit vectors, so let's say I call this as vector z corresponding to text t, and this I call as vector z corresponding to image I. And if they are not unit vectors, I can just do divide by magnitude of I and take the dot product of zi with zt and divide by magnitude of t. And this will basically be cosine of theta I t, where theta it is the angle between image and text representation. And if the vectors are very, very similar, the angle between them will be close to 0. And that would mean cosine of 0 will be 1. If the vectors are not at all similar, they will be orthogonal. Then cosine of 90 degree will be close to 0. So this is the idea. Now, you have already learned one way to convert your text into vectors in large language models. How do you convert text into vectors in large language models? What exactly did we do? If you can note down just the very first step. What was the very first step? How did we convert a text into, like, a word in a sentence? How did we convert that into a vector? Yes, we need tokenizer for sure. But we first need a dictionary, right? We need a vocabulary. So our vocabulary will have all the possible tokens that the language model will encounter. Now, if for simplicity we say that the tokenization is each word is one token, in reality, that's not the case. In reality, each token can be word or subword. But if we simplify and say that each word is a token, then the vocabulary will consist of all the possible words. Now, this vocabulary, let's say the first word is apple. Then there are a bunch of other words. Last words will be something else. Now each word will have an ID number 0, ID number 1, etc. And we also discussed that GPT-3 had around 50,000 tokens in its vocabulary. So it was like a relatively big vocabulary model. Now each of these tokens are represented by one vector. So token number 0 will have a vector associated with it. Token number 1 will have a vector associated with it. Token number 50K will have a vector associated with it. The dimensionality of this vector will depend on what your model is. So one of these was 768 dimensional model. It was the, I think GPT-3 model was 768 dimensional vector. And you can have any number of dimensions. So now if you are presented with a sentence like apple is a fruit, something like this, then the first thing you do is you will divide this sentence into tokens or corresponding token IDs. So let's say the token ID of the first word is 0. Let's say the token ID of this is 350. Let's say this is, maybe this should be 0, this is 10. And let's say this is something like 100, something like this. Then we look at our vocabulary or dictionary to see what is the vector associated with token number 10. What is the vector associated with token 350? What is the vector associated with 0, 100, and so on. Thus, we will get 4 vectors of 768 dimensions, and each of those vectors will correspond to one token. So this is how we got vectors associated with a text. And then one more thing which we did was we added position embedding. So if the first token is at position 0, second token is at position 1, third is at position 2, position 3, and so on, we added position embedding to get the final vector embeddings corresponding to all input tokens. And only then we passed all of this through multi-head attention to produce context vectors. So this will go through multi-head attention. This will pass through multi-head attention. Each tokens will produce one corresponding context vector. And that context vector also had same dimensionality as that of the input. So if this was 768, this was also 768. So we went through this process to produce vector associated with your text input. Now, by slightly different logic, how can you convert your image into a vector? So text conversion to vector is something that you are familiar with. How do you convert your image into a vector? One example you already know from the last lecture. In Vision Transformer, you knew how to convert image into a vector. What did we do? We divided an image into patches. Each patch was converted into a vector, which was the token. Then on top of that, you added position embedding. Then the position embedded tokens were passed through a transformer to produce the final context vectors, right? So that is one way. Another way is you can pass the image through a convolutional neural network without any attention mechanism or anything. You just pass it through convolutional neural network to increase the number of channels of the image and decrease the spatial dimension. Originally, the spatial dimension will be, can you please prevent from drawing on the screen? Otherwise, I'll have to remove you. I'll share the screen once more. So each image at the starting will be 32 by 32 by 3, something like that of dimension. So XY spatial dimension will be 32 by 32, and Z number of channels will be 3, RGB. And as the image passes through each convolution layers, the spatial dimension will start to shrink, which I will show you in a moment. and number of channels will increase. At some point, you can have the image represented by just one vector. And if the dimensionality of the vector embedding from the text and dimensionality of the vector embedding from the image, if they are of same number of dimensions, then you can directly construct the cosine similarity. So this is in a nutshell how you could imagine constructing a, you can imagine constructing a simple vision language model. Yes, if the image has multiple objects, what is done in reality is first the image is passed through an object detection model like faster RCNN or something like that. Then that model will give you potential region proposals within the image. And those region proposals are then converted into vectors, not the entire image. In our lecture today, we will not be using any region proposal network or anything. We'll be directly using one image with just one object. But in general, the image entirely is not converted into a vector. The regions within the image are converted into a vector. To know what are the regions that are meaningful, you use something like a region proposal network or faster RCNN. I'll actually show you a paper. So there is this paper called VisualBERT. And in this paper, what they did is for each image, they constructed rectangular regions. So just see this. So here, this is just one image, but then they have this red color rectangle, yellow color rectangle, blue color, etc. And I just want to show you one sub image. Just focus on this last layer 11 image. Okay. I know that there are a lot of things going on, but I'll just show you quickly what this is. So red color is man, blue is shirt, yellow is sidewalk. This light red color is pedestrian, and then this blue is sidewalk. Then look at the color of these rectangles. This color of these rectangles are matched with the color of these squares. So here, essentially what that means is this column is corresponding to image embedding of this person or this man. This column, this third column corresponding to this yellow color is probably, I don't know what is that, sidewalk. Then let's say this light red color is what? Pedestrian. So light red color is pedestrian, and you see using the light red rectangle, it is enclosing some other pedestrians that are walking. And now look at the last layer, what they are visualizing. So last layer is the rows are the words, which is a caption that describes this image. So the caption that describes the image is man wearing white shirt is walking on sidewalk alongside other pedestrians. So just read these words from top to bottom. It is just one sentence. So they have divided the sentence into words, but it's just one sentence. Man wearing white shirt is walking on sidewalk along other pedestrians. Now, what they tried to do was they built a vision language model to see how much does the word man correlate with whichever rectangle is corresponding to man. So which rectangle corresponds to man? Red rectangle. So ideally, for the word man, this rectangle, actually, let me take a screenshot so that I can annotate. Yeah, this paper name is called VisualBERT. So here, ideally, the text corresponding to man and the image corresponding to man, they should have the highest similarity. So this rectangle should have the most intense color. But here you can see that in the first layer, so third layer of the VisualBERT, this rectangle also has some high color. So that is man as the text, and this light red is what? Pedestrians. So basically, when the text encoder is looking at man, the image encoder is looking at pedestrians. But by the time you reach the last layer, look at the last layer and look at this. So now this is man and this is pedestrians. And look at this color where man as the text and pedestrians as the image, they are kind of intersecting. Here, there is no color. So by the time the model is into layer number 11, man is fully looking at just the man. See, this is the one with highest color. So the highest color is light color, like whitish color. So whitish color has 0.4 as the correlation score. If it is a dark square, it will be 0. So this is just the correlation map. And look at the mapping. Okay, I'll pick one more example. So let's say, okay, in the title itself, in the caption itself, they are mentioning a very good example. So the model also refines this understanding, incorrectly aligning man and shirt in the third layer. So let's look at third layer and how man and shirt are aligning. So third layer is this, layer 3, man and shirt. Which one is shirt? Light blue. So light blue, man and shirt are aligning. I don't see man and shirt aligning in third layer. Actually, I see shirt is blue, shirt is... Okay, actually, I don't see man and shirt aligning in layer number 3. Where is shirt and man aligning? Shirt is blue and man is this side, but here there is no alignment. This last one is pedestrians, right? So this is man. Oh, man wearing white shirt is walking along. White box, man and shirt is aligning. White and shirt. Yeah, white and shirt is aligning because white and shirt should align. I think they are, I mean, white shirt, it's okay. Dark means there is very little correlation. Bright means there is correlation. Let's look at another example. Let me just first remove these annotations. Which one should we take? Let us look at this one, this white. So this white is walking, the word walking, and pedestrians. So in layer number 4, the word walking and the image corresponding to pedestrians. Why is it pedestrians? Because this fourth column is pedestrians. That's why. Has very good alignment. But by the time you reach here, the word walking has very little alignment only with, I guess, man, because this is the row associated with the word walking. And the first image is man, second image is shirt, third image is sidewalk, fourth is pedestrian, and fifth is sidewalk. So basically, by the time of 4, the model is a little bit more, I would say, careful in producing the alignment. Yeah, walking and pedestrian should align. In my opinion, walking and pedestrian should align. But I guess it's up to what the model is learning. There was actually one very good example. Can you please explain layers and column? Yeah. So each row corresponds to the individual word in the sentence. So man wearing white shirt. So that is each row. So now imagine that each row is now converted into a vector embedding. Each column corresponds to these rectangles. These rectangles where objects are identified in the image. So rectangle with red color is man. You can see that it's a man over here. Rectangle with blue color is shirt. You can see that this blue rectangle is actually enclosing shirt, kind of. It's also enclosing white. Yellow is sidewalk. I don't know if yellow is actually really enclosing sidewalk, but whatever. Pedestrians is light red, and you can see that other pedestrians are in light red. There are 3 pedestrians. There are 3 light red rectangles. Okay. So now the word pedestrians, actually, let's look at the word pedestrian itself. That's the best example. We don't have to look at anything else. Just look at pedestrians. The word pedestrian should be corresponding to 3 these red rectangles, correct? Which means word pedestrian and this pedestrian bounding rectangles should align. So ideally, the score inside this cell should be visibly highest. But in some layers, it's not very high. In layer 3, it's not very high, denoted by the dark color. But by the time you reach the last layer, actually, you can see that this is pedestrian and this is pedestrian. It is aligning, kind of. And what are the other words? Side, other. So other means other people, right? So other word should also align with ideally pedestrians. And here actually there is no alignment in layer number 3. In layer number 4, there is no alignment. In layer number 5, there is some alignment. Layer number 6, very little alignment. Layer 10 has very good alignment. By the time you reach layer 11, there is very, very good alignment. So just look at the last 3 words and just look at pedestrian to understand how the model is learning to align the word embedding and specific image embedding. How is correlation calculated? You can simply take the dot product. That is one way to calculate correlation. We will look at that in today's lecture. Okay, so that is how you basically construct similarity score between vector embeddings corresponding to text and vector embeddings corresponding to image. I anyway plan to conduct a full-blown research paper review separately for this particular paper, but I just wanted to show you this because this is so beautiful. Okay, so in traditional AI, we know we have discussed this text input converted to text output, LLM next word prediction. Vision transformer was image input converted to class. Basically, you were using it for classification. In the last lecture, we did MNIST classification. VLM can ideally do both. It can take multi-model input, and this is useful for very many different tasks. If you show an image and ask a VLM, what is the person in this image doing? It's called VQA, visual question answering, or visual common sense reasoning, or image captioning. So all of this vision language model can do. In today's lecture, what we will be doing will be an image. We'll take an image and the corresponding captions, and we will see how to construct alignment between the caption embedding and the image embedding. And there are actually many different types of VLMs you can construct. Okay, unlike when you say vision transformer, you primarily think about the vision transformer paper, the one produced by Google. But when you say VLM, there are actually many papers that propose many different models of vision language model. It's not like just one thing. But as long as that model allows you to produce this thing like a joint embedding. So in this joint embedding space, what is done is the image, which is like this, and the caption. Let's say caption is happy dog running towards the camera. So this caption is actually, we know as a human, we know that this caption is aligning very well with this image, right? Then ideally, the vector embedding corresponding to this caption, this image, and vector embedding corresponding to this caption, they should be very close to each other. So here I'm just showing the tip of the vector. I'm not showing the vector line, but basically the vectors should align very much. So this joint embedding or joint representation space, and in that there should be very good alignment between image and text. That is the goal of a VLM, vision language model. Now we will come to the idea of NanoVLM. So while building this VLM, you will understand what exactly the architecture of VLM looks like. So there are a few questions. Basically, we can create VLM based on regions instead of patches. Exactly. So VLM, typically we don't feed patch into a VLM. We can do that. I mean, in vision transformer, it's anyway patches, and each patch, depending on the patch size, will only enclose a few number of objects. So yes, it is possible. Now most of your questions will be answered in this section when we build it from scratch, because here we will discuss what the data set look like, what kind of task our VLM is going to do, what the exact model architecture is in encoder for both image and text, and what's the loss function. So let us discuss this. So the task for which we are going to build the NanoVLM, and by the way, one more thing is, we are naming this as NanoVLM because of a very specific reason. The number of parameters here will be less than 1 million or close to 1 million. So if you look at, let's say, a small language model, it will have around 1 billion-ish parameters. But nano models, I mean, it's up to you. Like, you can name, I mean, if something has, let's say, 100,000 parameters only instead of 1 million, you could maybe call it as some other VLM, and you can say it's a nice VLM that you propose. So it's up to you. But here, when I say nano VLM, I mean a vision language model with just less than 1 million parameters total. Total number of trainable parameters should be less than 1 million. We will also, at the end of today's lecture, we'll hand calculate the total number of parameters to conclude that indeed our VLM has only less than 1 million. We'll calculate the exact number of parameters. Okay, so now the task description. What are we going to do today? So task description is, we will try to build a data set with images and corresponding captions. So we are going to build a synthetic data set today, and the task will be, if I input on the trained VLM, if I input a new caption from the validation data set, the VLM should be able to tell me which image is the most correlated image corresponding to this caption. So that is one type of task. So finding the most appropriate image from the validation image data set for any given caption in the validation data. The opposite task is, given an input image from the validation data set, the VLM should be able to propose, this is the best caption that describes this image from the data set. So these are the two tasks, both are kind of symmetrical. So on one case, you want to find the best image corresponding to your caption. In the other case, you want to find the best caption corresponding to your image. Now, here is a very specific word, NanoVLM, a tiny clip-style model trained on synthetic colored caption. I'll come to what is the synthetic colored shaped captions, but what is this clip-style model? So CLIP was a paper proposed by OpenAI. It is very famous. This is the paper. So this paper did not introduce the idea of contrastive learning for the first time. I'll tell you what contrastive learning is, but this paper utilized the idea of contrastive learning for teaching a vision language model to learn from text and image. And if you look at the authors, the last author you might recognize, Ilya Sutskever, one of the former co-founders of OpenAI. This paper has very high citations, around what, 60,000 or something like this. Yeah, 46,000. So very high citations this paper has. So some of the famous papers from vision language models, I recommend you to read if you want to read. One is CLIP paper. CLIP paper is actually very nicely written. It's very simple language, but it's a bit long. It's 48 pages. So before you start with CLIP, I recommend you to read VisualBERT paper. This is a relatively short paper, I think 12 or 15 or something like that number of pages. And its language is very, very easy to understand. So this is one paper which you should definitely read. Another paper is VisualBERT. VisualBERT has slightly more number of citations, around 5,000, cited by around 5,000 people. VisualBERT was produced just before VisualBERT was proposed. And in my paper reading workshop, I do plan to cover all these three. CLIP will be the most difficult one simply because of its length. But VisualBERT and VisualBERT, I'm hoping to be easy. So I recommend you to just read this quickly. It's not especially VisualBERT and VisualBERT, they are very easy to understand. One more paper, I'm sorry to recommend so many papers. One more paper I highly recommend you to read if you have the time is the BERT paper, original BERT paper, which came right after, I think in 2019, has very high number of citations, 150K. So BERT paper is also not that long. It's very, very nicely written. The language of writing is relatively easy to understand. So the order in which you can probably read, if you have the time and bandwidth, is you can first go through the BERT paper, and then you can look at maybe not VisualBERT, go through VisualBERT, and then go through VisualBERT, and then go through CLIP. So these four papers, I can put the link here. So first you can go through, where is this? Yeah, this one is BERT. So go through this first. Then second, go through not VisualBERT, because VisualBERT, in my opinion, is a slightly simpler architecture compared to VisualBERT. In VisualBERT, you will see the idea of cross attention between query from image and key and value from text. So here in this image, what they are showing is, so they had two streams, one stream for image and one stream for text. So usually for producing attention weights, we take query, key and value, everything from the same data set, right? But here what they did was query they took from the image and key and value they took from the text for here. And similarly for the text stream, query they took from the text and key and value they took from the image. So that is how they constructed this co-attentional transformer layer, this co-TRM. So it's like a very, very good idea. And last, fourth, you can read the CLIP paper. CLIP is actually written in a very nice, easy to understand language. Only thing is it's a little bit lengthy. Other than that, I don't have any issue. But in CLIP, they use this idea of contrastive learning. This is another paper. I don't think you need to learn contrastive learning, from the paper. It's not really necessary. But I'm just showing you this paper just in case if anyone is interested. So this contrastive learning of visual representation, what they introduced was, actually, let me explain it through Miro board. That will be better. So what they did was, let's say you have a bunch of images, okay? You have 1, 2, 3, etc. N different images of a dog, of a mug, of water bottle, microphone, pen, whatever, bunch of images. And let's say you have captions that describe those images. So these are now the corresponding captions. So this is image number 1. This is caption number 1. Then image number 2, caption number 2. So the image and caption ideally should align very much. Now, the way they constructed this data set, one smart way to do this is, for website, the images have alt tag, right? So image, if the website is not loading or something, you will see the alt tag. In Instagram, you might have seen it sometimes. So by scraping the internet data for images and corresponding alt tags, you can get a huge data set where image and corresponding captions are there. Many times captions may not align, but if the data set is very good, captions align really well. Now, what is done is in contrastive learning, the idea is you pass the individual items. So you have n data points. Okay. You pass each of these separately through text encoder to produce vector number 1. So this is a vector number 1 corresponding to first text caption, vector corresponding to second caption, third caption, and nth caption. These are not, this is not an n-dimensional vector. Please don't get confused. These are n vectors corresponding to the n captions. Actually, this should be capital N. Now, similarly, you pass this through an image encoder. This can be vision transformer or CNN to produce n vectors corresponding to images, image 1, image 2, image 3, etc. up to image n. Now, we know that corresponding to image 1, caption 1 is the aligning caption, right? Because image 1 is that of this puppy, caption 1 is Pepper the Aussie pup. So this image 1 aligns with caption 1. However, image 1 should not align with caption 2. Image 1 should not align with caption 3 or with caption n, right? So if you look at this from the dot product perspective, I1.T1 should be high, but I1.T2, I1.T3, all of these should be low, ideally. So this should be ideally close to 1. These numbers should be ideally close to 0, correct? Now look at it from the captions perspective. So this was from the image perspective, this particular row. But look at it from the captions perspective. Caption number 1 should align with image number 1. But caption number 1 should not align with image number 2. It should not align with image number 3 or n. Which means if you look at this column, the I1.T1 should be high, close to 1 ideally. But T1, when you take dot product with I2 or I3 or IN, it should all be ideally close to 0. And by the same logic, I1.T1 should be highest, I2.T2 should be high, I3.33, like this. This whole diagonal should be very, very big numbers. I mean, very big meaning as close to 1 as possible when you take dot product. Rest of the numbers should be 0. So this is called contrastive learning. Why is it called contrastive? Because these are called positive pairs. I1 and T1 are positive pairs. Those are pairs of images and text. So image and corresponding caption that are aligning. I1 and T2 are negative, I1 and T3 are negative, I1 and Tn are negative. Similarly, T1 and I2 are negative, T1 and I3 are negative, T1 and In are negative. So this is the idea of contrastive learning. So I1 and T1 should be aligned because in our ground truth data, image number 1 and caption number 1, they are the corresponding image caption pairs because we need a dataset pair. We need image and corresponding caption like that large number of dataset. N is not the batch size. Yeah, oh, sure, N can be batch size, but here N simply means you have N data points. You have N captions and N images. Now, one question you may have is, what if I have similar, what if let's say images that of a, so here it's a puppy. What if I have one more image of a puppy? Then maybe caption T1 will align with that, right? So ideally, when you construct the data, that is one shortcoming with this contrastive learning. So here we try to push I1 and T1 as close to each other as possible and try to push away everything else. T1 and I2 should be pushed away. T1 and I3 should be pushed away. So that is one side, I would say, one negative aspect about contrastive learning is that if there are two images that are similar, or if there are two captions that are similar, then the model is a little bit rigid. Model will not try to align those, the image and the similar caption. Model will look at the exact caption. But the good thing in CLIP paper was, in CLIP paper, they used 400 million data points from the internet. Somewhere in the paper, they are mentioning that 400. Yeah, see, so they used 400 million image text pairs. And just because of the sheer volume of the data, this shortcoming of contrastive learning was not an issue. It won't be an issue for us also. I will show you why when we construct the data. And correlation is simply calculated by taking dot product between two vectors. I1 is a vector, T1 is a vector of same space. So I1.T1 will be like the dot product. And what is the goal here? The goal is, if I go back to this image, the goal is to push these two vectors as close to each other as possible. But this and this should be farthest away as possible. This and this should be far away. This and this should be far away. Similarly, this and this should be far away, this and this should be far away, this and this should be far away, because these are all negative pairs. But in this particular example, these two are positive pairs, but this is a negative pair. This is a negative pair. All other green-red pairs are negative, but these two are positive. So the goal is to align positive pairs and push the negative pairs as far away as possible. Now, let us look at how to construct, how will the loss look like? So let's say I have one image number I, okay. Now I have n captions to compare this against. So caption is TT for text, TT1, T2, T3, etc. Right? So ideally, image number I should match really well with text number I, and image number I should not match really well with any other text, because I should have high cosine similarity with TI, but I should have very low cosine similarity with all other T's. So one way to construct like a probability distribution, if we were to take dot product of I1 with T1, I with T1, I with T2, etc., this dot product will be probably close to 0, but let's say 0.1, this may be 0.1, this may be 0.2, and this may be 0.9, and the last one might be 0. something 2. But this should be the highest number. I and Ti should have the highest dot product. Now, how do we convert these set of numbers into a probability distribution? I have now a set of numbers. How do I convert numbers to a probability distribution? I simply take softmax, right? So what I can do is e raised to I Ti divided by sigma e raised to I Tj, where j runs from 1 to n. So now this is the softmax score corresponding to the matching positive pairs. Now let's do one thing. I have a small Excel sheet which shows the softmax number. So this is just an example. Let's say I have now 3 similarity scores between, let's say, this is, let's say, Ti, this is some other pair, this is another pair. So consider that these two are negative pairs, this highlighted blue ones. This is a positive pair, and these are the similarity scores, which is the dot product between the vectors, 2 pair of vectors. Now I can take softmax of this, and when I plot it in softmax, look at what has happened to my softmax. So this is the original distribution, 0.1, 0.2, 0.8. But when I took softmax, the softmax actually became less sharp. You see, softmax distribution became more even. But usually we don't like this, because this even, that's not the point of taking softmax. We don't want this even distribution. We want sharper distribution. We want the model to be able to say, yes, with very high likelihood, the third item is the positive pair. First and second items are negative pairs. So then what can I do? I can simply mathematically, if I divide, let's say, I and Ti by number like 0.1, will my softmax become more sharp or less sharp? More or less? It will become more sharp, because the value inside the exponent is now increasing. So, and that's because this number is less than 1. But if this number was 10 instead of 0.1, it will become less sharp, right? So this parameter is called temperature. So we can denote it by some tau or T or something. Ti divided by tau by sigma j equal to 1 to n e raised to Tj divided by tau. Okay, so now this is the temperature value, which is called as temperature, but essentially it's a parameter that we introduce whose value can be like between 0.01 till 0.2. I mean, these are thumb rules. There is no specific rule. It should be generally less than 1 for it to work. So we'll introduce this also. So this can give you a very sharp softmax distribution. So here the third plot in the Excel sheet, I have introduced a temperature parameter of 0.01. And you can see that now the softmax is very sharp. These two are negligibly small. It's not even visible because those values are like close to very close to 0 when you take the softmax of the 3 numbers, because my temperature is very small. But if the temperature is like 0.2 or something, see, the sharpness has reduced, but still it is reasonably sharp, right? So this is the reason why there will be one temperature parameter in the loss. Now let's think of one more thing. So this was the case where I was trying to be mapped with T1, T2, etc. up to Ti. But same thing can be said for Ti also. Ti, if I look at it, this has I1, this can be compared against I2, this can be compared against II, and so on. So I can construct a symmetric version of the same thing by saying, so this is, let's say, the loss, not loss, similarity, softmax similarity score or probability distribution when you are looking from I image to text. But I can construct something like same thing for text to image, softmax text to image. The only thing that I have to do here is e raised to ti ii by tau divided by sigma j equal to 1 to n e raised to ti ij divided by tau. So it's just that in the denominator, the instead of tj, it will be ij. That's it. So you are iterating through all the n images instead of all the n texts. But that's not it. Like this, how many ti do I have? I have n number of ti's, correct? I have n, I have t1, I have t2, t3. So I can compare t1 with all possible images. I can compare t2 with all possible images. I can compare tn with all possible images. Similarly, I can compare I1 with all possible texts. I can compare I2 with all possible text, and I can compare I3, In with all possible texts. So now, if I want to have a loss, how can I convert, by the way, a probability distribution into a loss? Because here, higher the probability, the loss should be lower, right? If my softmax probability score for the positives are high, I should have a low loss. What should I take? Just taking logarithm is enough, negative log, right? Because if my numbers are between 0 and 1, and for positive pairs, let's say my score is 0.99, softmax score is 0.99. And then if it is 0.99, we should take a negative log, because negative logarithm of 1 is 0. Negative logarithm of a small positive number will be a very high positive number, because log 0 is minus infinity. This tends to be minus infinity. Log of 1 tends to be 0, which means if I take negative of this, negative logarithm of a small number, let's say 0.001, will be a big number, a big positive number. Negative logarithm of, let's say, 0.999 will be a very small positive number. Let's say this is 0.00, something like this. This is, let's say, 99. I'm just writing a random number, okay? But I hope you get the point. So what we have to do is we have to take the negative log of softmax. So negative log of this guy. This I can call as similarity score between II and TI. This. So negative log of e raised to II TI divided by tau by sigma j equal to 1 to n e raised to II j, not jj, tj, text j by tau. So this is for image to text, and like this we'll have text to image. But then I have to do one more thing. I should loop it through all possible images because I have n number of images. So I can simply say sigma, where I goes from 1 to n, and then minus 1 by n. So this is now a mean. So I hope you are following me. What we are simply doing is I have n images and n captions, correct? Every single image can be compared to every single captions. Similarly, every single caption can be compared to every single image. If I am comparing ith image with all captions, the loss will be negative logarithm of e raised to image number I compared with positive pair divided by, this should be t. positive text pair T from, and then j equal to 1 to n e raised to I t j by tau. This is for just for the ith image. Like that, I have to do for all images. So I simply do minus sigma I equal to 1 to n, 1 by n. So minus 1 by n times this, right? So this is basically now the loss function L, loss function I to T, image to text loss. Like that, I can construct same opposite version like L for T to I, text to I. And then I can add these two losses and take an average, half. So then basically the loss, contrastive loss or clip loss, I should rather say, clip loss equal to 1 by 2 times Li to T plus Lt to I. This is basically the clip loss. This is also called symmetric loss, and you simply take an average. You can or cannot take average. It's up to you, because ultimately at the end of the day, you just care about having a loss that is based on the contrastive pairs and positive pairs. All right. So this is the clip loss, and I will show you the formula which you may have seen before. But this is the Li to T exponent of xi. So now x is image, y is text. So xi t yi is basically transpose. So in vectors, you take transpose, A transpose multiplied by B is how you take dot product between A and B. So that's why you see this T here, transpose, divided by sigma. So here sigma is the temperature, sigma is the temperature. And this sigma I equal to 1 to n is because you are iterating over all the images. And then negative logarithm because you want to convert softmax into a loss score. Softmax because you want to convert the dot product similarity scores into a probability distribution. So think about all the things which we did. We first said similarity is equal to dot product. Then we said to convert dot product to probability distribution, we need softmax. Then we said to convert softmax to loss, we need negative logarithm. Then we said we have to take this not just for the ith image, we have to do it for all. So we just did sigma I equal to 1 to n, 1 by n. Then we said we need symmetry. We need to do the same thing for text. So basically, we do the same where image and text are swapped. Loss have twice the diagonal dot product. Yes, so diagonal dot product will be occurring twice, but the remaining ones will not occur twice. That's correct. Because let me go back to this image. If I delete all of these annotations, in image to text loss, you are considering all these items, right? And text to image loss, we are considering all these items. So if you now look at this I1 dot T1, the positive pair, it is getting counted twice in the loss function. So that is true. In this formula, we have taken softmax, this exponent, this is the softmax. Why? What does this mean intuitively? Intuitively, it means you want image number 1 to align with text number 1 if you compare with all the possible text captions. Similarly, text number 1 should align with image number 1 if you consider all the possible images, right? Because sometimes you may want to search a good caption for a given image, or sometimes you may want to search for a good image for a given caption. I'll give you an example. Let's say you ask, let's say you want to do an image search. You have a database of a bunch of images, and you are running a jewelry shop. And in your jewelry shop, you have a bunch of jewels which have names. And now I come to you and I say, I need something that looks really good for a diamond square cut ring, something like that. Then that is the caption that I'm providing you. And from your database, you should find the best possible image for that caption. In another case, I may come to you and say, hey, here is my ring. Here is the image of my ring. What is the name of this actually, according to you? And then maybe you want to tell, I mean, it's a made up example, but I hope the example makes it clear why you need image map to text and text map to image. But this is the loss function that we'll be using. Anyway, I'm coming to explain the loss function in detail. I was coming to explain this in detail later, but I already explained it. Now, what is our data set? This is very interesting. So first of all, I wanted a simple data set, because if I use some big data set from Kaggle or somewhere else, it will take forever me to train. So what I thought was, I will create a data set synthetically, image caption pairs. Now, what my data set looks like is I have different colored objects. So I have 9 different colors, red, green, blue, etc. Then 3 different shapes, square, circle, triangle. Then 9 different positions where this shape can occupy the image. So center, left, right, top, bottom. Then top left, top right, bottom left, bottom right. So totally, now I'll have 9 times 9, 81, 81 times 3, 243 images, right? And captions that I'm constructing will look like this. So these are now the synthetic images that I created. So this is pink circle top, because this is like a circle. It's a low resolution image, which is why it does not look like a circle strictly, but it's a circle of pink color. It's at the top of the image. Center is somewhere here. That's why, although it does not look like top, it is top. Now, second image is brown circle occupying bottom right. So these are different images I plotted as a grid, okay? Just don't get confused since there is no boundary. So this is one image, this is another image. So this is now the caption, this is the corresponding image. This is the caption, this is the corresponding image. So this can be constructed programmatically. So I will share the code with you today so that you can also create it synthetically just by running the code. So totally you will have 243 unique image caption pairs. Now, what's the difference between this and, let's say, a bunch of images with labels as cat or dog? What's the difference between those two? Here you have 243 images and a bunch of labels. In a classification task also, you have a bunch of images and they have labels. So what's the difference between this and that? Complex caption. The main difference is that here you don't have repeating labels, right? Because every image is unique and every caption is unique. So can you technically train just a CNN classifier here? You can't, because you don't have multiple images belonging to the same label, right? If you were to call the caption as a label, you have 243 images and 243 labels. So it will now become a 243 class classification with just one image per class. Can you build a classifier? No. So there is very much difference between the thinking of these captions as labels. This is not labels, okay? But labels for a image classification between cat and dog will be, you will have bunch of images that are cats, bunch of images that are dogs, and captions or labels of every single one of those dogs will be just dogs. Caption or label for every single one of the cat will be cat. So corresponding to cat label, you will have bunch of images. Corresponding to dog, you will have bunch of images. Here, that is not the case. So this is not a multi-class classification problem at all. So please don't get confused. Then what we do is, we have 243 images in the data set, which we will split into training and validation. So 80% for training, 20% for validation. So it will be a very small data set, and let's see how well we can train this. Then I want to go through the overall model architecture. So overall model architecture looks something like this. So what are the negative images? Negative images are simply the wrong captions. The correct caption pair, image pair. So let's say I take this image. This is brown circle at the bottom right. So this brown circle bottom right caption and this image will form positive pair. But this image and all other captions will form negative pairs. This caption and all other images will form negative pairs. So now what our model architecture for today will look like is, we will build, so today we will not be using vision transformer. We want the training to be a bit faster. So we will use CNN-based encoder for constructing vector representation of these images. So by the time it reaches here, the image reaches here, it will look like a vector of, let's say, 64 dimensions or something. And this text we will convert into encoded version, basically another 64 dimensional vector. And now you can compare these all these 64 dimensional vectors with these 64 dimensional vectors using CLIP-like contrastive loss, the same formula which you saw, exponent of dot product divided by sigma exponent of dot product. So now this is the vision part of the VLM, and this is the text part or language part of the VLM. And what will happen is, if this VLM is not trained very well, this vector and this vector will not at all be correlated. I will actually show you one image, which anyway you will get at the end. So look at this. So this is a 64-dimensional embedding of my vectors. So this is before training, and this is after training. Okay. And look at the correlation. So dot product between, so now I just use the color map for showing 64-dimensional vector. Otherwise, I can't display it. Now this color map correspond to the numbers, and you can see that there is very little. So if you compare dimension 1 of the text and dimension 1 of the image, it's not comparable. This and this not comparable. This and this not really comparable. So overall, when you look at the pre-trained image embedding and pre-trained training text embedding, they are not very similar. And because of that, the dot product here is very low, 0.0369. But after training, you look at the similarity. They are not looking exact, but there is a lot of similarity. Like this and this look similar, this and this look kind of similar, this and this look kind of similar, this and this look kind of similar, then this and this look kind of similar. So the similarity is much higher, and the similarity score is 0.8873 in this case. So this is what we are trying to do. What we are trying to do is we are trying to align the image embedding and text embedding through CLIP loss. So we will train the image encoder and text encoder so that the alignment can become better and better and better after training. What do we mean by better? The dot product between two positive pairs should be very high. Here is another example where I, instead of taking 64-dimensional embedding, I took 3D embeddings. 3D embeddings we can try today. And this was the embedding, how the embedding was looking. I don't have the cosine similarity score here, but this is how it was looking before training. They were, and these were for two positive pairs. So for same image and caption. So this was one image, and this was the corresponding caption. They were having no alignment. They were pointing in kind of different direction. And after training, you see, they have very good alignment. They both are kind of pointing in similar direction in the 3-dimensional space. So this is what happens when you train the VLM to produce better and better embeddings through CLIP loss. So this is our goal today. We want to build something that can do this. Okay, so now let's come back. Okay, this we discussed. Now let's look at the image encoder separately. So image encoder, what we are going to build today is a CNN. We can use vision transformer and use the last, the 0th CLS token, class token for the as the final embedding. But let's keep it simple. Let's use a CNN. Now I'll show you how the CNN architecture look like so that you all understand what happens to the image as it passes through different layers. So the image resolution is very small. It's 32 by 32 image. So it will be looking very pixelated, but it will have RGB channels, 3 channels. So input image will have 32 by 32 by 3. Then what happens in the next layer is, by the time image reaches the next layer through convolution, it will become spatial dimension will shrink to 16 by 16, and number of channels will expand to 32. Now, this we had discussed in detail in the last lecture, but I want to refresh our memory. Tell me, for this to happen, let's say I am using a 3x3 kernel, okay, 3x3 convolution filter. What should be the padding and what should be the stride? Padding equal to what? Stride equal to what? If I want to get this kind of an output. My kernel size is 3x3. So kernel size is 3. Okay. Padding equal to 0, stride equal to 2. Padding just stride equal to 2. For those of you who think stride should be 2, why should it be 2? What's the logic behind stride equal to 2? The logic is that when you are taking, instead of stride equal to 1, if you take 2 pixel jumps at a time, the width dimension will get reduced by half, height dimension will also get reduced by half. And that is what is happening. 32 is becoming 16, 32 is becoming 16. So stride should obviously be 2. But padding, what should it be? Padding, should it be 0 or should it be 1 or something else? There must always be padding. See, think about this. If stride is equal to 1, okay, padding equal to 0, will the dimension remain or will the dimension shrink? It will shrink by 2 on the along the width and 2 along the height. So you have to have one padding of 1 pixel along the top, along the bottom, along the right, and along the left, which means there has to be a padding if you don't want dimensionality loss if stride was 1. So here 32, to preserve 32 as 32, you should keep stride equal to 1 and padding equal to 1. If stride was 1 and padding was 0, 32 will become 30, right? Because you are losing 1 pixels, 1 row on the right, 1 on the left, 1 on the top, and 1 on the bottom. Now tell me, how many channels should my filter have? Number of channels for my filter. Is it 3 or is it 32? My question is number of channels for my filter. The answer is 3, because this, you should never forget this diagram. Actually, let me show you here. This is my image and my filter acts like this. Like this, like this, like this, like this. So never forget this. This is how the filter acts. So whatever is the number of my input, okay, whatever is the number of channels in my input, same number of channels should be there in the filter. What should be the number of filters in this convolution? What should be the number of filters? There should be 32 filters, because filter number 1 should produce this output. Filter number 2 will produce this. Filter number 3 will produce this. Filter number 32 will produce this. Okay, so I have 3 channel filter of kernel size 3 by 3 of and like that I have 32 filters. Now tell me, how many learnable parameters does this make? If I have one kernel with 3 by 3, how many learnable parameters are that? Just 3 by 3 kernel means number of parameters is 3 multiplied by 3, 9 parameters, right? But then I have how many such channels? How many 3 by 3 kernel channels do I have in the input? I have 3 of them. But like this, I have 32 filters, correct? So these many learnable parameters will be there, but there will be one more set of learnable parameters. There will be one bias parameter per output channel. So how many output channels are there? 32 output channels are there. And if there is one bias along each output channel, I'll have another 32 added here. So total number of learnable parameters, okay, when you go from here to here, will be whatever this number is, 3 times 3 times 3 times 32 plus 32. Why is this 32 coming? What is this 32? It's the 32 filters. What is this 3 by 3? It's the kernel size. What is this 3? It's the number of channels. What is this 32? It's the number of bias parameters, because you have 32 filters. Each filter has one bias term. Now, next is simple. From here to here, how many channels should be there at the input? If you go from here to here, spatial dimension is shrinking from 16 to 8. How many channels should be there at the input? It should be 32. Number of channels at the input is equal to number of channels, number of channels in the filter is equal to number of channels at the input. So the filter should have 32 channels. Kernel and kernel padding stride, they will remain the same, because 16 is becoming 8. So kernel will be 3 by 3, padding will be 1, stride should be 2. Then number of filters should be how many? 64, because output channel, there are totally 64 channels in the output. So now how many learnable parameters will that be? I have a 3 by 3 filter, but this filter has 32 channels. Like that, I have 64 filters, and for each filter, I need a bias. So these many learnable parameters will be there. Now, same logic applies from here to here. 64 becomes 128, 8 by 8 becomes 4 by 4, 128 becomes 256, 4 by 4 becomes, 64 becomes 120, and then 4 by 4 becomes 2 by 2, 2 by 2 becomes 1 by 1. But the 1 by 1 logic is different. I will tell you what is happening. So you have actually 4 convolution. This is convolution number 1, number 2, 3, and 4. All of this, we are using kernel size 3 by 3. Padding is 1, stride is 2. So 32 becomes 64 means 2 filters. No, 32 becomes 64 means, so I'll show you once more. Here, let's say dimension is 10 by 10 and channels are 3. And if I want to produce 6 channels at the output, okay? If I want the output to be something like this, let's say 5 by 5 and 6 channels, what should be my filter dimension? If filter kernel is 3 by 3, let's say each of these are 3 by 3, I should have 3 channels because input has 3 channels. I should have padding equal to 1 and stride equal to 2. Stride equal to 2 because 10 is becoming 5. 10 is divided by half. But since I have 6 channels at the output, I should have 6 filters. So first filter will go like this and produce. So first filter will do that to produce whatever numbers are present in this. Second filter is responsible for, so this is the second filter with 3 channels. It is responsible for this. Sixth filter is responsible for this. Now, if I had 64 channels, I will need 64 filters. If this number was 32, each of these filter will have 32 channels. So that is exactly what is happening here. When you go from 32 to 64, your input number of channels is 32. Your output number of channels is 64, which means number of filters should be 64. Each filter should have 32 channels. Okay. Okay, so we have 4 convolution operations. But following this, we do something called global average pooling, GAP. I will show you how to implement this, but basically you have 4 numbers here, right? 2 by 2 means you will have 4 pixel values. You will take an average of those 4 numbers just to produce one number. And number of channels actually is not changing. This 128 is over here. Okay, don't get confused. So this is 128. This is 256. And global average pooling does not change the channel dimension. 256 will remain 256. But this is global average pooling. Okay, it just averages these 4 numbers to one single number. And then now you have a 256 dimensional vector. But if your input dimensionality is, let's say, 64 input embedding, let's say your embedding space has to be 64. How do you go from a 256 dimensional vector to a 64 dimensional vector? What would you use? You will simply use, you can use a feed-forward neural network multi-layer perceptron, but basically a matrix multiplication, right? And how many trainable parameters will this be? Okay, before that, how many trainable parameters are this? Global average pooling. Who says it is 4 times 256 or something? Global average pooling number of parameters should be 0 because you don't need any trainable parameters to take an average of 4 numbers. It's simply those numbers summed up divided by 4. So global average pooling or max pooling, those operations does not introduce any additional parameters. Now let's think about how many parameters you have when you go from 256 dimensional vector to 64 dimensional vector. How many trainable parameters? 256 times 64, and how many bias terms? 64, because each dimension at the output can have one bias added to it. So these many number of trainable parameters, and then you do layer normalization, plus you convert, after layer normalization, you convert it into a unit vector, the magnitude to be unit vector, so that when you take cosine similarity, maximum possible value will be 1, minimum possible value will be 0. Okay, so then what else? Yeah, one more question. In layer normalization, what exactly are we doing? Layer normalization does this. If xi, this is the input, ith input, and here let's say it is x1, x2, etc. up to xn. Okay, first thing is I'll take the mean of this, which is mu, standard deviation of this, which is sigma. Then I will say xi equal to xi minus mu divided by sigma. This is one step. Now, are mu and sigma learnable parameters here? So first of all, by doing this, if I do this, the new set of xi, what will be the new mean and new standard deviation? What would this be? Mean should be 0. Standard deviation will become 1. But are mu and sigma learnable parameters or not? They are not. They are not learnable parameters. Those numbers are byproduct of just mathematical calculation on these numbers. Now, what you have to do is something called scaling and shifting. So essentially, what happens to xi is xi minus mu divided by sigma multiplied by beta I plus gamma I. Beta and gamma, I don't know what the terms are in literature. You can call beta, gamma, delta, whatever. But essentially, you do a scaling and you do like a bias term. So you will have two terms. These are now learnable parameters. You will have two terms associated with each dimension. X1 will introduce 1 beta and 1 gamma. X2 will introduce 1 beta and 1 gamma. Xn will introduce 1 beta and 1 gamma. So by that logic, now how many learnable parameters will your layer normalization introduce here? It will be, how many of you think it should be 2? If you say 2, why is it 2? I have a 64-dimensional vector. For each dimension, I need a scaling factor. I need 1 beta and 1 gamma. So total number of learnable parameters in the layer normalization will be 2 times 64, so 128. Now we can calculate currently, but maybe let's push it to the end of the lecture. So by the same logic, now we can calculate how many trainable parameters my image encoder has. Right? And like that, I can do for text encoder to calculate the total number of trainable parameters. And that will be the definition of whether my model is nano or micro or whatever. So that we can do at the end. But now you know the logic. Now let's move on to text encoder. Text encoder is actually much simpler. So the use of gap step is, so gap is, you ultimately want just like, one number in each dimension because you want a vector. Now, how do you convert a 2 by 2 into 1 by 1? Either you can take a mean, or you can simply take something like a padding 1 stride equal to 2, 3 by 3 convolution. That also is fine. But the problem is if you do that, you will have more number of learnable parameters. If you simply do global average pooling, it does not introduce any parameters. You can do average, you can do max, anything is fine. Because this is anyway experimental. I only made up this architecture. So it works very, very nicely. So I decided to keep it. We can try max pooling also instead of average pooling. But now answer one question. In which, so if I have convolution 1, 2, 3, 4, in which of these convolutions do I have the maximum number of trainable parameters? Is it in 1 or is it in 4? It should be here, because here the number of learnable parameters will be something like 64 times 3 times 3 times 128 plus 128, something like that, right? So the more the number of channels here you have, the higher the, it's not a general rule, but in general, in this case, fourth convolution operation will introduce the most number of learnable parameters. So if you had a convolution operation here also, it would have introduced again even more number of learnable parameters. So ideally, you want to reduce the further convolution operations. If you want the model architecture to be small, I could have introduced a 2D convolution here also, but then I can do the calculation. But my guess is learnable parameters. Then if I had a convolution here also, this guy will have the highest number of learnable parameters. Then maybe my model will not be nano anymore if I want less than 1 million parameters. We'll see that. Okay. Now in text encoder, the interesting thing is I had experimented with 2 types of text encoders, one with attention, multi-head attention, and one without multi-head attention. So text encoder part is very, very simple. First, let us think about our dictionary. Okay, let me go back to our captions. Look at the caption. Pink circle top, blue circle top. So the captions are created based on the color, space, shapes, space, position, correct? So in my vocabulary, that way, how many unique tokens will be there according to this logic? What will be my vocabulary size? For those of you who are saying it is 21, what is the logic? Those of you who said 21, they are correct. Actually, it's not 21, it's 22, but the logic behind 21 is correct. See, vocabulary is basically tokens. This is not a token. This is a sentence. When I tokenize this, I will take only the words. So totally in my dictionary, blue will be there. So if I consider this sequence and this sequence, number of unique tokens are not 6. Number of unique tokens are pink, circle, blue, and top. It's only 4. So the total number of tokens will be this. This will introduce 9 tokens. This will introduce 3 tokens. This will introduce 9. Plus, I can have a classification token also, CLS token also, just like how we did in the last lecture. So total CLS token plus or class token plus these 9 tokens, these 21 tokens, my dictionary will be totally of just 22 tokens. That's it. Right? Now, that is let's come back to the text embedding. So now I need some sort of way to convert 22 tokens into 64 dimensional vectors, correct? Because each token is now 64 dimensional. And what kind of matrix can I use for this? What kind of matrix can help me convert a vocabulary in which there are 22 items into 64 dimensional vector, any given one? I can use an embedding basically. I can use an embedding whose dimensionality will be something like, let's say 22 by 64 or something like that. Basically into the embedding, into the vector embedding function, I will have to pass the 22 and I will have to also pass 64. 64 is the embedding dimension of each vector. 22 is the number of vectors or number of tokens in my dictionary, in my vocabulary. So we will need that. Then how did we usually construct context vector? My context vectors were softmax of key times or query times key transpose divided by square root of dimensionality of the key space multiplied by value, correct? This was my context vectors. And what was this? This was attention weighted average, or let's call it as maybe attention weighted sum. Both are fine because those weights are anyway less than 1. But basically, we are taking attention weighted sum of what? Context vectors are equal to attention weighted sum of dash. Context vectors are equal to attention weighted sum of dash. Value vectors, because these are attention weights. And I'm taking a attention weighted sum of value vectors to get context vectors. In the simplified attention, what we did was we took softmax of x dot x transpose multiplied by x itself. We did not use query key value. In a simplified sense, we can choose not to have query key value also, which means no attention is needed. We simply take the dot product. So one thing which we can do is a very simple thing is, let's say my token is blue square top. Now I have to convert this into, and then I should have a CLS token also. And in my dictionary, CLS token may have index 0, blue may have an index of 5, square may have an index of 3. I'm just putting random numbers here. Top, let's say it has an index of 17, something like this. Now, what I can do is, and then these indices will now be converted to 64 dimensional vectors, correct? Each of these are now 64 dimensional vectors. If I had a multi-head attention over here, MHA, these would have become context vectors, correct? This will be 64-dimensional context vector. This will become 64-dimensional context vector. This will be. And then what I could do is I could simply take just like how we did in vision transformer, I could simply take the classification tokens representation, whatever this guy is. And I can compare now this with what? What will I compare this with? 64-dimensional embedding of my image, right? So then I can compare this with 64-dimensional embedding of the image. This is if I have multi-head attention. If I don't have multi-head attention, a simple thing which, this is just a trick. It happened to work because my data set is so small. What I did was I just took an average of these. So I added these 4 things up, no attention. I just added these and divided by 4 and said that is now my final context vector. Although it is a weak context vector, it's a 64-dimensional context vector. Then I can simply compare that with the 64-dimensional vector, which is corresponding to image. So we can try both. In one case, we can use multi-head attention. In another case, we'll use no multi-head attention, just simple averaging. In both cases, I'll show you how it works. Text encoder is that, but code we'll come to in a bit. Loss function, you guys already know what the loss function is. Loss function is simply the same symmetric clip-like contrastive loss. What else is there? That's it. I think now we are ready to go. Let's start coding. Loss alone, should I explain? Okay, so loss is basically, I have now my images circle, blue, red circle top. So I have a bunch of images which are looking like this, and I have captions. So captions, let's call it as XI. Images, I call it as YI. Now my L to Li to T, image to text, is equal to -1 by n, sigma I equal to 1 to n. Then exponent of Xi transpose multiplied by Yi divided by tau, tau is the temperature, divided by sigma j equal to 1 to n, Xi Yj, exponent of Xi Yj by tau. This is Li to T, Lt to I. So here we are taking, first we are taking the dot product for similarity. Oh, I forgot to put the logarithm, log of this. Then we are taking this exponent. What is this? What is this guy? Inside the bracket, it is softmax. What is this? What are these? They are cosine similarity, rather dot products. Why do we have log here? Softmax probability scores are all between 0 and 1. So see, what is our goal? My positive pairs ideally should have, what will be the softmax score corresponding to my positive pair? Softmax score will be 1. It should be 1 once the model is perfectly trained. For negative pairs, softmax score should be 0. Correct? Which means the loss, if my positive pairs are producing a softmax score of 1, what should be the penalty I induce into my model? I should not have any penalty because it's producing the perfect possible softmax score. Now, how can I convert 1 into a 0, into a loss function? I can simply take negative log. Negative simply because logarithm of any number between 0 and 1 is a negative number. So, but loss should be positive. So I just put a negative sign. So negative log of 1 is equal to 0. So I don't penalize the model at all for producing a softmax score of 1. But let's say I have a positive pair. Okay. I'm looking at a positive pair whose softmax score is equal to 0.1. Tell me, is this a good model or bad model? Why is it a bad model? Because for positive pairs, the probability, softmax probability score should be as close to 1 as possible. Which means, should I penalize this model very heavily or not penalize very heavily? We should penalize it heavily because the softmax score is really bad softmax score. Now, if I take negative logarithm of some number, and let's say that number is a small positive number, 0.1. This will be, let's say, x. Negative log of, now let's say in another case, I have softmax score of 0.001 for positive pairs. This is model A, this is model B. Which model should get more penalty, model A or B? Okay, so now negative logarithm of 0.001 is equal to y. Which number is greater, x or y? X or y? Some people are saying x. It should be y. This is the logic. Okay, tell me log of, what is log of a raised to b? It's equal to b log a. What is log of 10 raised to minus 3? It's minus 3 log 10. What is negative log of 10 raised to minus 3? It is 3 log 10. What is negative log of 10 raised to minus 1? It is negative, it is log 10. Which one is greater, this or this? A or B? 3 log 10, 3 log 10 is greater. And what is 10 raised to minus 3? 0.001, this guy. So this y is greater than x, which means you are penalizing model B more than you are penalizing model A, as it should be. So that is why we are taking logarithm. And then we are simply, where is my formula? Then what is this 1 by n? Why do we have this 1 by n? Sigma equal to 1 to n and 1 by n. Why do we need this? Because you have multiple anchors to consider. So that the term for that is called anchor. So the image I is the anchor here. You are comparing it with other pairs to see which one is positive pair and which are negative pairs, right? So you have n number of anchors to consider. Like that, symmetrically, you will have LT to I, text to image. Just that instead of x, you will have y. X and y will be swapped. Then you take your final losses L equal to LT to I plus Li to t by 2. So this is your final clip loss. Contrastive, I don't want to call it as clip loss, but essentially that is what it is. Clip-like loss. Clip is contrastive language image pairs. That is what we have here, language image pair. Okay, now let's start coding. Please open your Google Colab. And today, in fact, we won't be coding every single line from scratch because that will take at least 3 hours. But we'll code the main parts from scratch. Main parts are image encoder, text encoder, and what else? Clip loss, those 3 parts. So I can share the code with you in 2 ways. Maybe I'll share this link with you. That might be easier. Yeah, I think you can just copy the code from this link time to time instead of a GitHub gist. Let's do that. So first is imports. We need some imports. So import math random for random number generator, then import torch for PyTorch. This is not a classification task, right? Why do we say it's a classification task? Because we don't have classes here. We have actually 243 images. Yes, if you want to call it as a classification task, it's like 243 classes, but it's not a classification task. It is, you have unique captions associated with images, and somehow you have to create embeddings corresponding to image and text that should align. And then while searching for the best possible aligning image, you can simply search based on the embedding. All right, torch, then torch.nn as nn. This we will need while constructing the classes. One more thing that we will need is torch.nn dot functional as f. So I'll tell you why this is needed. This is later needed for constructing unit vectors. After normalizing the vectors, we have to make it into unit vectors. So that's where we will use this. This you have seen from Vision Transformer. Basically, we pass nn.module into every single class. Then import torch.utils.data. Actually, from this, we import dataset. So from torch.utils.data, import dataset. Then data loader for creating batches. Then from Python image library below, import image. This is for drawing to construct our images, image and image draw. I don't know if anything else is needed, we'll figure out. Then import matplotlib dot pyplot as PLT. For now, we just need those. If we need any more, we'll figure out. So just, I recommend you to write this along with me. That will be the best experience. But if there are parts where I copy paste the code, in those places alone, you can simply copy paste from my code. But here, I think since I'm typing, you can follow it with my speed. Okay, no module torch dot. Okay, import torch comma. Okay, next is we should have some variables that we define. So let's say variables, image size, how many pixels, let's say 32 pixel image. Then embedding dimension, let's say it is 64. And attention heads, number of attention heads, if we have multi-head attention, is 4. Then batch size 12. This we can change, of course. Then while training, we can train for like, let's say 10 epochs. Then learning rate, LR, let's say 3 times 10 to the power of minus 4 or something like this. And for clip loss, we should have temperature parameter. This we can put anything random between 0 and between 0.01 and 0.2 or something like that. So we can put any number here. If we need anything else, we can define one more thing, device equal to torch.device CUDA if CUDA is available, otherwise CPU. This is just this we can keep it separately, but let's keep it here. So variables is done, and then synthetic data set. Set properties. So here I have what? Colors. Then I have shapes. Then I have positions. And this, in fact, I can copy paste from my other code. That way, this I don't have to spend so much time. So there are 9 colors, then 3 shapes, and 9 positions. So these are the properties of my synthetic data set. Then next is drawing image shapes. So you can access from this Google Colab notebook, right? Or is it not updating on a real-time basis? This link, is it updating on a real-time basis? If not, I can share this also, but let me know if it is updating. Okay. Okay. Now let's draw the shapes. Define draw sample. Sample is like a sample data point, and this is just a function. What we need to pass is we need to pass color, we need to pass shape. So it's not shapes or color. We are passing one color and one shape and one position at a time. And image size also we can pass. Image size, we'll pass the variable that we had defined earlier, 32. And then we say image equal to image.new of color should be RGB. Then XY dimension, I mean width and this dimension should be whatever is this image size. So I can copy paste this twice, width and height dimension. And then canvas should be white color. Then after this, we say draw equal to image draw dot draw. And then we pass this into this. And now let's see a few things. Now the way I'm drawing is like this. So I have a 32 by 32 sized image, but my canvas will be slightly smaller than that. So I will say my canvas is, I'll put a margin. Okay, so then this I will call as W, width of the canvas, and this I will call as H, which is height of the canvas. Not this, this is just the from here to here. And then I have to define a square, which looks like this, whose width is W by 2 and height is H by 2. And if my object is on the left side, I will say this is the canvas, the white color canvas in which I will draw. I will draw the object. The total canvas is of width W and height, but this square is where I'm going to be drawing my shapes. If it is at the left, if it is at the right, I'll be drawing over. This is so annoying. If it is at the right, I can draw here. If it is at the top, I will draw like here. Bottom, I'll draw here. Now for drawing, I need to define 4 coordinates. One is the top boundary along y-axis, bottom boundary along y-axis, left boundary along x-axis, right boundary along x-axis. So this is called as y0, y1, x0, x1. So for draw x0 and x1. So for drawing the shapes, I have to define these things. Now tell me if my object, okay, if my object position is top, whether it is top left or top right. For all of these 3, my y-axis will not change. My x-axis will only change, which means my y0 will be how much? What should be my y0? Actually, it's not 0. It's 0 plus margin, because I'm defining a margin also. I'm drawing slightly inside my image. Small margin is there. So basically, for all of these cases, my y0 will be margin. What about y1? It should be margin plus whatever is the size of this small square. It is h by 2. So margin plus h by 2. Then similarly, if let's say my object is somewhere here, okay, so my object will be drawn inside that small square. Tell me what is the x0? What is x0 in this case? X0 will be margin plus x0 is this. It is margin plus whatever is this. This is actually w by 2. X1 is, what is x1? X1 is not width minus margin. Width is this. Width is this guy. This is image size. So x1 should be image underscore size minus margin. Or I can say it is margin plus W. I can also say that. That's also fine. And what is Y naught? This. What is Y naught? It should be margin plus quarter of the size of this, not half. So it should be margin plus H by 4. And Y1, what is Y1? Margin plus H by 4 plus H by 2, which is margin plus 3 by 4H. Right? So this, by this logic, we can define the 4 coordinates for all the possible cases. Okay. I'm not going to write all of them here because that will, I mean, all of them manually here, that will take a lot of time, but that is what we have here. So we can define a margin. So margin equal to 6 pixels, and then height equal to width equal to image underscore size minus 2 times margin, because margin is there on left and right. Margin so that the object is not going all the way till right or all the way till left. I can remove margin also, but I think that will be, drawing margin will be cleaner. That way, when I plot the images in a grid, it will not look weird because of closeness. But there is no physical reason why I cannot have a margin. Of course, I cannot have a margin also. I can keep it 0 also. And then these are now the X coordinates. So this logic is exactly what I discussed, but quickly go through it. If position is left, then X0 is margin, X1 is margin plus width by 2. Now it doesn't matter. So this is only for X coordinates. For Y coordinates, I have a separate. But then look at all these three. For all of these, it doesn't matter whether something is top left or bottom left or left. For all of them, X coordinates does not change. Y coordinate only changes. So see, this is X0 plus margin, X0 equal to margin, X1 equal to this. Same for this and same for this. Because X coordinate is independent of whether something is top or bottom or center. And same here, as long as something is right, it doesn't matter whether it is right or top right or bottom right, there X0 and X1 will be the same. And then for center, okay, let's discuss only that case. What if my object is at the center? What should be X0? X0 should be margin plus 1/4 of the width, margin plus W by 4. This will be margin plus W by 4 plus W by 2, which is margin plus 3W by 4. Same for height. Height will be margin plus height by 4. And this will be margin plus height by 4 plus height by 2, which is margin plus 3 height by 4. So that is this guy, X coordinate. Now Y coordinate also has same logic. So it doesn't matter for Y coordinate whether something is left or right or center. As long as it is top, its Y coordinate, Y0 and Y1 will be similar. Y0 and Y1 are these two, Y0 and Y1 are these two. This is also the same. Same logic. As long as something is at the bottom, it doesn't matter whether it's at the bottom or bottom left or bottom right. It's just the bottom. So Y coordinate is not affected. And then center coordinate. So this is the logic. So I'm going to just copy paste this part so that we can save some time. Once I write this, I will share the code with you. And then we can simply say, if shape equal to square, draw dot rectangle. So rectangle is the most general form of square. And then we pass these four. Fill equal to whatever is the color. And where is this color coming from? We are passing the color over here. Then passing the shape here, passing the position here. So color equal to that, outline is black. If shape is circle, again we define the limits, but then circle will be drawn inside that. Fill is whatever is the color, outline is black. For triangle, there is an exception. You need coordinates of, you're mentioning coordinates of 3 points rather than the bounds. So first point for triangle, it will be like this. If you are drawing a triangle inside this, 1 point will be x0, y1. This will be x0, x1, y1. And this will be x0 plus x1 by 2, y0. these are the 3 points you have to pass. And that is what we are passing here. Draw.polygon of actually this x0 plus x1 minus x0 is same as if I just delete this and keep this as plus, the same thing. So this is how we can draw these polygons. So I'll paste it here and that's it. Then you return the image. So return the image means that image that is created, which was defined here, will be created. So I'm just going to share the code with you. Maybe I can share here. So you can find the code from this GitHub gist. All right. Now let's just run this. Nothing will happen because we are not yet, calling the function. We just defined it. Then we need, so this is just the image draw function, but we have to call it in a little bit loop fashion, right? Because we have 9 shapes, 3 shapes, 9 colors, 9 positions. So let's write the code for calling the function multiple times. Class for calling class for building our data set. So then we say class shapes dataset. The first item will be the init constructor, define __init bracket. And to this we are passing the self, which is the current object that we are looking at. Self is the current object's reference. Then we say self.images. So we construct an empty array for appending images one by one. We construct an empty array for appending captions one by one. So that each time when we construct an image by calling this function, and when you get the image returned, you save the image here. Self.images and self.captions. And then we say for C in colors, you loop through all of that. Then for P or S in shapes, you loop through all the shapes. Then for P in positions, you loop through all the positions. Then we say image, which you are getting from this function, what was the name, draw sample or something. So now you have to call the function here. Image equal to draw sample, but here we pass C, S, P. Image size you don't have to pass because it's already there is a default value there. And caption equal to, for constructing caption, we need a dynamic variable. So this will be 3 things, right? First is whatever is the color, second is whatever is the shape, third is whatever is the position. So now this will be like a dynamic string. You are saving the caption as a string. And then you say, okay, now once these things are, actually you have to append also. So then you say self dot images dot append. And here you have to convert the image into a torch compatible format. So what you can do is you can just, let me just take this code alone so that I can save some time. So here essentially what, okay, numpy as empty. So just have that also, because here numpy is not getting recognized. So now we are creating the image and we are appending it here. And what we are doing is permute 201 is it will convert it into R, G, B format, and values will be between dot float by 255 values will become between 0 and 1. Self.captions.append.cap is to that array you are appending your each floating point caption, not floating point, a string caption one by one. Then you go out of the loop and then you say self. Okay, now you have to have a vocabulary builder. So first let's write that. So define build vocab, because you have 22 unique items. to be defined inside the vocab. I don't know why there is an error here, maybe because I'm not define init. Yeah. Define build vocab and words. I need words and I need to add those words to vocab. And I need the words to be converted to indices. Yeah, I know that I'm missing two things here. I will add that. So self, and one more thing is we need to add, which is the text that we are passing here. So let's say text, and we need to convert words to indices. So words to index equal to, we need that. And then we can return two things. One is we can return vocabulary itself and word to index. You'll see what this word to index will do. Now, what are the words? The words are, first we need to do this for actually there is a short form that I had written here. I will show you what the short form is doing. So can you tell me what is happening here? This is one line, but bunch of things are going here. What's happening here? So first is we have the incoming text. So for T in text, we are doing T dot split. So T in text means you have bunch of captions and you are picking it one caption at a time. So this is 2 for loop, one inside the other. So you first loop through all the possible captions. You have 243 unique captions. So T in text means each T will be one caption. But then T dot split means you will split the caption into the 3 words. 3 words are color, shape, and position. So now W is nothing but those individual words. So now what is being stored in a sorted array is the word W, and only unique items will be stored here. So here we can print these words. I'll show you what these words look like. So words is basically, actually, you know what? I can just let me comment this for a moment and I'll show you what this looks like. Dataset equal to shapes dataset, and then I can say not yet. I need data loader, but let's continue here. Words equal to sorted. So these are now the sorted unique words in alphabetical order. And then I will say vocabulary is nothing but words plus one more thing. Yeah. So this is for defining a set, correct? So you are appending to a set whenever there is a unique item coming. Now words, you are adding one more item to the words, which is CLS token. So then you say words plus CLS. Actually, CLS should be like this, because this is the CLS token. You are putting it in quotes, and then you are putting it in a bracket because you are adding it to your words. And then word to indexes, you can create another set. Actually, let me copy that from here. For every word, you are creating a word to index pair. So for every word I, W, you are basically enumerating your vocabulary. So whatever is the item number 0 will be CLS. Actually, you know what? This should not good. I should put here. I want CLS to come at the beginning. So CLS should have the index number 0. Then remaining items will be alphabetically. So A should be, I don't know if we have any color or something starting with A. A or B. B is there, blue is there. IJKLMNO. So maybe I think the after CLS, perhaps this might be the next token. Blue might be the next token. We'll see. We can print it and see that. Okay, then we have to call this vocabulary builder somewhere. So we say self.vocab, comma self.word to index. Word to index equal to self dot this function of, and then to this we are passing all the captions. So all the captions are in this self.captions. So that is the vocabulary builder. And then we need something that can encode the text. So define encode text and pass self here. And here we are passing one text at a time. So define encode text of self comma text. And then we need to create tokens. So tokens equal to so I need one token for CLS and one token for all the words in my input. So let's check the code. So one token for CLS, then one token for all the words in my input. So whatever incoming word is or incoming caption is, that will be split into tokens, and those tokens will be part of this talks tokens, and then CLS will also be part of that. And then I can just return tokens. But it should be like a tensor format. So return tosh.tensor. And then I think that's all. We don't need anything else. Define get item. Yeah, we can. If you want to print one image to see how the image looks like, define get item self comma idx return, and then this should return image and the encoded text. And I think that's it. If we need anything else, we'll add on the go. So this will hopefully build the shapes data set. Let me share this in GitHub gist. I'm adding it at the bottom. So please don't, I'm leaving a space between. So just take it from here. So this is that class. Okay, now I think we are ready to create the full data set. All right. Full data set is equal to, it should be an object corresponding to this class. And then I need a variable for storing what my vocabulary size is. So vocab size is equal to full ds dot, what was the variable? Vocab dot vocab, and I need the length of that, len of that. And if I want to see the vocabulary size, I can just print it. And hopefully this should print as 22. If it is not 22, something should be wrong in the code. So that will be a sanity check. Okay, something is missing. Shapes dataset has no attribute called bill vocab. Indentation, yeah, define init. Yeah, I think so. Yeah, thanks for that. Yeah, it was, I had an extra indentation to the right, so I just put it to the left. So vocab is fine, vocab size. Let's print the vocabulary also. I should then see if I print this full vocabulary. First word should be CLS, second should be blue, if I'm not wrong. Yeah, first second is blue, bottom. So this is like an alphabetically ordered vocabulary. So in my vocabulary, there are 22 tokens. Okay, so that is good. So now we are good to move on. So our data set creation is done, but we can print some data set. But before printing, let's create training and validation data. So train val data creation. So train size should be equal to whatever is the length of my data set. So whatever is the len of full DS, well, let's say 80% of it. And then val size should be 20% of this. Or let's say len of full DS minus train size. And now we can create the random split. So train DS comma val DS equal to random torch dot utils dot data dot random split. And here we pass the full DS and then mention the train size and val size. I think that's it. Shape's dataset has no len. I need the length of the full dataset. And where is that? Images, maybe. Or not vocab. Vocab is 22. I need the length of maybe captions or something. So shape full dot captions, perhaps that should be 243. What shapes data set has? Oh, full DS. I am not sure what's going on. Let me print this. Okay, length is 243. And if I try to do this 0.8 times, and I need an integer, not a float. So if I do this, it should work, right? Val size. What's the issue with val size? Okay, okay, got it. So it should be about this int of len we should define in the class. That is a good suggestion. I think I had it earlier. I think I had it here. Yeah. I think that was the issue. I should return self. Yeah, sure. That's a good suggestion. Whoever suggested, thank you. So now hopefully it should work. But here I don't need dot captions. I just need len of full DS. Now what might be the issue? Yeah, I'm already taking length, which means but how about this? If I just print, so this seems to be perfectly working. Len of full DS. This seems to be perfectly working. And I can assign it to something. And B equal to this minus int of this. So B equal to len of this minus A. And if I now print A comma B, I should get something, right? Okay, it seems to be, this seems to be perfectly working. I am not sure what exactly, if I copy this. Len of full DS minus train size. I have no idea what is the issue here. Let's ask Gemini. No, it should not be length of vocabulary, right? Because vocabulary is fixed irrespective of whether I have 300 images in my data or 200 or whatever. Vocabulary is 22. So we should not take vocabulary. We should take rather, okay, now it's working. What's the difference? Let me just check. Object of int has no length. What did change right now? I'm not sure what changed, guys, but whatever. I don't want to spend time here. I would rather spend time in the coding part of the encoder. But anyways, now let's pick data loader. So train loader and val loader. So here is where we define the batches. So data loader, this we had done in the last lecture also when we coded transformer. So here we pass train DS and here we pass val DS, validation data set. But then we have to say whether what should be the batch size. So batch underscore size is equal to batch size and shuffle equal to true for training, and shuffle, we don't want to shuffle for validation. It's not needed. So this is now the data loader. Okay, so far so good. And I can just now show you a random sample. So this one I don't necessarily want to write. Display sample data point. So now let's see if our images are working. Not enough values to unpack. Let's run everything to see if images, comma captions. Okay, so 243 images are split like this. Not enough to unpack. Okay, let's ask Gemini, which will give us the fastest answer. Okay, so blue circle to the left, it is fine, correct? brown circle top left is correct. So these are, now we are displaying random images just for sanity check. Yellow square top, gray triangle bottom right. So seems like most of the image types are getting created. Orange triangle bottom right. So everything seems to be correct. I will do one thing. I don't know till where I share the code. I will share the display code with you. Train size much greater than full DS in trains split line. Okay, that was earlier. Okay, but this you guys can also run. I hope the rest of the things you got. Train loader, this part is fine. I don't think rest of the things are fine. Okay, so our data set is good. It's working. So now what should we do? We are ready to now write the encoder. So first, let us go about image encoder. And then after this, we will write text encoder. And then after that, we will write clip loss. And then we will do training. And then we will check validation. That's it, right? Okay, so now start the fun part. So define, or rather class image encoder. And here we pass nn.module. And then define the init constructor self. Let's delete this. I will add this later. The super constructor, super is calling the init constructor from the nn.module. So basically parent class is different. We are inheriting bunch of properties. So this will call the init constructor of the parent class. Now we'll decide what all things to pass here. But before that, what was our architecture like? We had 4 convolution operations, right? And then following that, we had max global average pooling. Then we had projection. So let's write it. So self dot convolutions equal to nn dot sequential. Why? Because we are adding operations sequentially. Then first is nn dot con 2d. And here we have to mention total number of channels for the first convolution layer was 3. Output number of channels was 32, so we need 32 filters. Kernel size was 3. Stride was 2. Padding was 1. Then following this, we have another one where input is 32, output is 64. Remaining are the same. Then here input is 64, output is 128. Remaining are the same. And then input is 128 and output is 256. Now, one crucial thing that is missing here is, can anyone mention, there is one important thing that I'm missing here. The important thing is activation. So let's add ReLU. All right. Then that's it. For convolutions, that's it. Then we need, after convolutions, there is a global average pooling. But for that, we don't have to define a function. We can just operate it on the go for all the inputs. Yes, we can check without activation also. Then we need a projection. Self.projection equal to nn.linear. So it will be a linear projection from 256 to whatever is the embed dimension, which means I have to pass the embedding dimension somewhere here. Embed underscore dim equal to embed dim. So embedding dimension we pass, and then self dot normalization we need layer norm, or just norm, layer norm 1 equal to nn dot layer norm of, and these many, along these many dimensions we are defining the parameters. Now that those are the functions, but now we have to define the forward pass. So define forward self comma x, and here we do the actual implementation of the convolution. So we say x equal to self dot convolutions of x, Then x equal to, we have one more thing to do, but I'll do that after adding the projection. So self equal to x dot projection, self of projections of x. Yeah, indentation. Thank you. Then x equal to, so here we use this guy. We had defined a torch.nn functional as f. So here we say for converting this into a unit vector. So x equal to f dot or f of dot normalize of self dot norm of x. Self dot norm of x was, or layer norm 1 of x, comma, along column dimension. So along dimension or last dimension equal to -1. Then return x. But here I'm missing again one thing, important thing which we discussed, which is CAP, global average pooling. And that we have to implement before we project into our embed dimension, because in our diagram, global average pooling was, the projection happens here. Global average pooling happens before projection. So it has to, we have to write it here. So then what we need to do is x equal to x dot mean of, so first dimension is channel dimension, second dimension is x dimension, third dimension is width dimension, height and width dimension. So we take a mean of along dim equal to 2 comma or 1 comma no 0 1. I'm not sure if it is 1 comma 2 or 2 comma 3. Let's try both. We'll first try 2 comma 3. If this is the issue, it will be 1 comma 2. But basically, I need to preserve channel dimension. I want to do average along the individual channels for all the individual channels. Okay, I think that's pretty much it. I don't think I'm missing anything. If we are missing, we'll figure out. So first is the channel dimension. So I don't think 0 should be there. My only doubt is should it be 1 comma 2, or because there is a batch dimension also. Yeah. So yes, first dimension is batch, second is channel. So 2 3. So it should be 2 3. So I think this is correct. Next we can write text encoder. So class text encoder of nn.module. So this should inherit properties from nn.module. And then we say define then init constructor underscore underscore init underscore underscore self, then super underscore underscore in dot underscore underscore init nn dot sequential spelling. Okay, yes, sequential. Yeah, thank you. Okay, actually, let me run this to see if there is any other issue. Okay, yeah, now it's working. Init, then, so first we need token embedding. So self dot token embedding. Then I need self dot position embedding. This is equal to something. This is equal to something else. Then after position embedding, we need multi-layer perceptron. So self dot or multi-head attention, not multi-layer perceptron, MHA. And then after this, we need layer normalization. So self dot norm. Then what else? I think that's it. Among this, the easiest one is MHA. So this will be nn dot multi head attention of, and multi-head attention for this we need the embed dimension. And what? One more thing. What else do we need in multi-head attention? attention heads. So maybe I can call it as num heads. And then this we have to pass. So embed dim equal to embed underscore dim. And num heads equal to, if I remember correctly, I called it as attention heads underscore heads. Okay, and self dot token embedding should be nn dot embedding. And what should I pass here? I need to pass two things. So this is slightly different. So here we are creating token embedding for every single item in the vocabulary, not just for the context window. For this one particular line, for position embedding, it's for the context window. So here we need the vocabulary size underscore size. So this is a crucial difference. Vocab underscore size, comma, each item in the vocabulary is that of embed dimension. Embed underscore dim, which means I have to pass vocab size somewhere. Size is equal to vocab underscore size. Okay, so that is done. Then position embedding, again, also this should be nn dot embedding. But what should this be? What two things should I pass to position embedding? One is obviously embed dimension. Another is the context window. Context underscore window. What is the context window size? It is not 3, it is 4. Because CLS is also there. So context window is equal to 4. Okay, so that we pass. Then self dot norm is simple, nn dot layer norm along embedding dimension. So those are the functions. Then we can define forward pass. So define forward pass. Into that we pass self, and earlier we used tokes for tokens. So we can consistently follow that here, although it's not needed. Now let's see what all things we need. We first have to create token embedding, and then we have to add position embedding. So first let's do this. Can you tell me what will this be? What will be the value of this? Shape will be like what all things will be there in tokes dot shape. So this is the text encoder, right? So one dimension has to be the embedding. So let's go back to our notebook. See, one dimension has to be what is that? The embedding. Another dimension should be the sequence. So let's actually write it in this way itself. N comma L is equal to tokens.shape. And then one thing we have to do is, in the last lecture, if you remember in Vision Transformer, we had expanded the position embedding in a certain way so that we have that many number of position embeddings. So in position embeddings, what we want is, by default, what we will have is something like this. If let's say L equal to 4 and N equal to 2, what this means is you have two sequences of length 4. Length 4 because you have CLS token followed by 3 other tokens, and you have two such sequences in the current batch. So ideally, you want something like 0, 1, 2, 3 repeated 2 times, because position embedding should not change. Position embedding is position number 0, position number 1, number 2, number 3. Same for the next batch. So what we use is a code that looks like this. So first we create a range of numbers. So a range is a range of numbers whose maximum length is L. And L we will get from the shape of the tokens. So L is the total number of sequence items in the sequence, which is 4. And into that we pass the device. The reason why this device is passed is in case we were running on GPU and we did not pass anything for the device, by default this range of numbers are created using CPU. But if our tokenization before was done in GPU, then that will cause a conflict. So it's better to pass whatever it was the device as device equal to tox.device. Then third thing is unsqueeze of 0. What unsqueeze of 0 does is it creates an extra dimension. It adds one more dimension based for the batch, and then expand n comma L means it will add. So if batch size is 3, it will expand it multiple times. So same thing will be repeated n number of times. I'll just use the code as such. So x equal to or position embedding equal to torch dot range of L comma device equal to docs.device, whatever device was used while creating the tokens, and dot unsqueeze of 0 to create an extra dimension, the 0th dimension, and then dot expand n comma L. And then we need position embedding to be added somewhere, plus now to create tokens. Okay, let me explain one more line. Self. So now this token, can you tell me what this tokens will contain? What this talks will contain? Let's say I have a batch size of 2. Size equal to 2 and sequence length L equal to 4. And what will this talks contain? It will have, of course, sequence of tokens, but the question is what that sequence will look like. Will it be the vectors or will it be something else? It will be the IDs of those vectors. It will not be the actual vectors themselves. So these numbers will be simply integers, 0, 17. It will go from 0 till maximum will be 21 because the dictionaries, the vocabulary size is max 22. So it will go from maximum 21 will be the index. Now from this, we have to get vectors corresponding to these IDs, right? So for that is why we had defined earlier this nn.embedding. So from the vocabulary, a particular ID item will be converted into a vector of the embedding dimension. So what we can do is we can pass tokens into this self.token underscore embedding. So pass tokens here, and then we say token underscore m equal to this. And then you can actually add position embedding on top of this. So now you have not yet, but position embedding, this is just position embedding ID, but you should pass that to this because position embedding also should be vectors of dimension 64. Currently, this will simply be 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, but that has to be converted into position embedding vectors. So you pass it through here. So an easier or simpler way to write that is position embedding. This is position embedding ID. Then position underscore embedding underscore vectors is equal to self.position embedding of this. Then token embedding vectors is equal to, or to make it even clearer, token embedding underscore IDs is equal to tokens. But to convert this IDs, token underscore embedding underscore vectors is equal to you pass the ID to create the vector. Then final embedding is equal to token embedding vectors plus position embedding vectors. So now this is the final embedding, and this final embedding goes through multi-head attention. So then we say final embedding equal to self.mha of and we have to pass this 3 times. This we had discussed last time. Oh, argument is there any mistake? I think, yeah, position embedding IDs. We should pass position embedding IDs here. Thank you. So final embedding will be, you have to pass this 3 times. The reason why you have to pass this 3 times is because query key value has to be created from input. So it's not always from the same input as you saw from the VisualBERT paper. Sometimes query and key can come from elsewhere. So that's why you pass it 3 times. And the output that you are looking at is at the 0th index. So 0. And then you have to do normalization. But before that, we have to do one thing. What is that? Now we have the context vectors. This is actually, let me not call it as final embedding. Let me call it as context vectors. That will be better. Now what should I do? Which one am I going to use? Which context vector? I'm going to use CLS tokens context vector. So that will be final underscore token equal to context vectors of 0th item. So this is the batch dimension. This is the 0th item in the sequence. Now what we have to do is we have to do a layer normalization. But before that, usually in vision transformer, you might remember there was a classification head which was projecting it into the final dimension required, which was projecting the context vector into the final dimension required. So if you look at this image, this MLP head was the classification head. So we can add one like that just to be consistent with how other models are. So projection is equal to final token of yes, we should transform to unit vectors also. So we should pass the final token into a projection. That projection we have not defined yet. So self dot projection of some input dimension. Let's write what this is to output dimension. Output dimension should be the embedding dimension. And here input dimension also happen to be embedding dimension simply because our multi-head attention is not changing the dimensionality from input to output. So this just happened to be embed dimension. Final dimension should be anyway embedding dimension because we want to compare this with image. But here input dimension to the projection layer just happened to be embedding dimension. That's all. It's not always, it need not always be the case. So then we pass to the projection layer. So what do we pass to the projection layer? The final token. And then after this, we do the normalization. So then we say output equal to f dot normalize of self dot projection should be nn dot linear. My bad. Yeah. Output dot normalize of self dot norm of projection, comma dimension equal to -1. We have to do it along the column. So that's it. I think we are good to go. The problem is we are using too many variables. Now that you know what these variables are for, we can simply do the following. X equal to, let me delete this. So I'm just going to simplify. Now that you know what all of these things are, just this tokens I will use here. Then I'll remove this. Now you know these are the context embedding vectors. Then final embedding I'll call as x. X is equal to token embedding plus position embedding. Then I'll pass x here, x comma x comma x. That is equal to x. And then final token also I will call as x equal to x of 0. Then projection equal to x equal to this of x. Then output x equal to of x. So this way it's a bit clean. And then return x. So that's it. That's it for the text encoder. I hope it should run. Okay, it is running. Then the last thing, it is we'll look at the text encoder without attention, but currently it is with attention mechanism. Next is last thing, clip loss. Now clip loss is just a function clip underscore loss of, and here we need to pass image embedding, text embedding. So this code I will share in the GitHub gist, or I guess you can just refresh also, should be fine. And then temperature. Then first we need logits, and then logits can be used against targets to construct the cross entropy loss. And there is loss from images, then loss from text. Then what we can return finally will be average of these two, I plus loss due to text by 2. Now let's say logits is equal to basically the dot product. So image embedding multiplied by text embedding dot t divided by temperature. Then, okay, now let's see. X equal to, so this is, you are taking the only the CLS token, which is the token number 0. First index is corresponding to batch, but for every batch among the sequence of 4 items, we are taking the 0th item. So that's why X equal to X of colon comma 0. Just to extract the CLS token, so that that token's representation we will use as the final embedding, final text embedding. And that text embedding will be compared here against the image embedding. Okay, so now target should be what? Can you tell me what the target should look like? What I mean by target is, let's say I have a batch of 12 images. For first image, which caption is the ground truth? For image number 1, caption number dash is the ground truth. Caption number 1. For image number 10, caption number 10 is the ground truth. So targets will be basically 0, 1, 2, 3, etc. up to 10. So for image number 1, targets will be first item, target will be first item in the targets array. For image number 2, the target will be of the index number, second item in the targets array. So basically, and this is because my image and caption pair, I don't need to know what is the caption. I just need to know the index of the caption in my targets. So this is how we will align. So targets will be torch dot a range of, and here whatever is the number of images, so image embedding dot size of 0, that many range of numbers I need. And then here also we have to pass the device. So device equal to image embedding dot device. So that whenever we create this torch dot arrange, PyTorch by default Python creates it in using CPU. So if we are using GPU for rest of the computations, if we don't pass this, it will cause a conflict. Then loss is simply f dot. F we had defined earlier by during the imports, cross underscore entropy. And here we compare logits against targets. Now, you might have one question, where is softmax applied here? Softmax is implicit, it's inside the function. So here we are not having softmax, okay? We are passing logics and targets. Softmax is part of cross entropy loss in Python. Now, one more question. Now for loss with respect to text, what should I pass here? So let's say I'm taking text number 3, right? What should be the, what should be the ID of the corresponding image target? If I'm taking text number 3, it should be same as 3. So targets need not change. The target array can still stay as exactly what it is. So this can remain as it is. But instead of passing now the logics, I have to pass the transpose of the logics. Why? Because just go here and look at the clip loss image. Where is the image? So in one case, you are comparing all these items. In another case, you are comparing all these items. So the logics corresponding to your image are found in the column. The logics corresponding to, text are found in the column. Logics corresponding to image are found in the row. So if you want to access the ones in the column, you can simply access it by taking transpose. So we can send pass logics.t here. And I think that's pretty much it. Nothing else. Okay, so now we have defined most of the things. Now, only remaining thing is the model, then data optimizer. This we can define vocab size we already have. So image encoder equal to image encoder dot to device. Then text enc equal to text encoder dot to device. And parameters that we are going to now optimize during our training will be whatever parameters are there in both of these encoders. So I can just say list image encoder dot parameters plus list of text encoder dot parameters. And those are the params that we are optimizing. Then optimizer equal to torch dot optim dot. Then these parameters we are optimizing, and learning rate equal to, we had defined it earlier as LR, I think. Yeah, LR. Target need not be .t. So that's what I'm saying. See, targets should be simply those numbers 0, 1, 2, 3. Image number 1 correspond to text number 1. Just like that, text number 1 corresponds to image number 1. So targets, we can just pass the same targets. Okay, so this much. Okay, so now it's working. Now we can simply run the training. So now we don't need to write the training part of the code. It's anyway for all models the same. Let us do one thing. Let's display some embeddings before training so that you'll see how the embeddings look like. Some random embeddings. Text enc is not defined. Let's run it here itself so that variables are matching. Yeah. So I'll share this full code with you. I think here I have defined some other variables compared to what this function is. But just look at this. What we have is, we have this image and this caption. So this is orange triangle top. And look at the embeddings before training. Before training, embeddings look completely different. there is very little, if you compare it dimension to dimension, there is very little similarity. Very few dimensions are exactly matching. And then I have a training loop. So this part I'm not interested in writing. It's just training through different batches and printing the accuracy. And you can see validation loss is decreasing continuously. And let's see the embeddings after training. Look at this after training. It's very, very, I mean, I'm not saying exactly similar, but it's much more similar than earlier. And then the dot product, the similarity looks like this: minus 0.51 before training and 0.9197 after training. We can do one thing, keep number of dimensions to be just 3 instead of 32. And let's look at how the embedding looks before and after training. Oh, embedding dimension should be divisible by number of attention heads for sure. So attention heads, let's keep it 3. So now text encoder, yeah. So now this is how the image looks like before training. Slight difference is there. Yeah, temperature, of course. So yeah, very important. Temperature value will definitely make the dot product loss different. Lower the temperature, higher the penalty for making mistake. See, here I have plotted it into, so this loss, look at this. These are negative pair, positive pair. Now, if I want to penalize the same negative pair more, all I need to do is reduce the temperature, 0.001. Oh, 0.01, let's keep it. Yeah, see, now when I kept it 0.01 for the same mistake, the similarity score has not changed. For the same mistake the model made, we are penalizing the negative models more and positive model less. So this is the 0.01 temperature, but if it is 0.2, it will not get penalized that much. So I'll do one thing. I'll directly share this with you so that you can just run it yourself. Yeah, just take this code. This is full code. Now after, so this is before training, and if you run this once more, it will pick a random other example. See, this is completely different, right? So this is a very different. If I plot this in 3D, actually we can do that. Ask Gemini to create a 3D plot of these vectors. Create a 3D plot of these 3-dimensional vectors as arrows before training. And let's run this to see how the 3D plot looks like. So this is how the 3D plots look like between image and text embedding. This is before training. There is, of course, cosine dissimilarity between them. And after training, the same 3D embedding. So you see why the validation loss is not decreasing so much. It's because the expressive power is less. It's a 3-dimensional embedding. In 3-dimension, you are expecting to capture all the information in your image and your caption. It's not easy, right? That's the reason why validation loss is not at all decreasing very much. But final embedding is actually very bad. Let's run once more. Okay, post training, this is how it looks like. Cosine similarity before training is 0.52, after training is 0.96. And the 3D plot before looks like this. 3D plot after, we can plot one here. Create a 3D plot like this for after training. Yeah, so this is after training. See, much closer. Those two embeddings in the same 3D space are now much closer than before. So this plot actually tells a lot of story, right? It's very it's simple to see, but it's very, very good. Let's come back to 64 dimension. I want to show you one last thing before we wind up. So embedding dimension, let's keep it at 64. The last thing I want to show is the image fetching for a given. Oh yeah, so this error is because for the 3D plot, I should not provide more than 3 embeddings. So I should just comment, it works only if the number of embeddings are 3. Otherwise, maybe we'll have to take 3 principal components or something like that. And attention heads, yes, thank you so much. Attention head should be 4 or something divisible, something that divides 64 perfectly. Last thing which I want to show you is this. So this is the image. Brown triangle center is completely wrong. Green. Okay, there is huge mistake here. Green triangle bottom right. Actually, the model is not at all good. Let's see what is happening. Green circle top. I know what might be happening. I think I have messed up something in the code because embedding is not coming out correctly, but this is easily fixable. Comment 4D text, 4D text encoding. Where is that? Yeah, I think this is because this is a text encoder class without attention. Yeah, we added 4 convolution 2D. This is correct. This part is fine. No issue. But I think somewhere, let me just restart the session and activation is there. So ReLU, nn.ReLU is there. But what is missing is something else. I initially thought batch first equal to true, that was missing, but that's not the case. It is added here. Actually, here I did not add that. I was about to ask you to add that later once our error is so high. Here, you remember from our last lecture, we had not in position embedding in multi-head attention. Here we had a batch first because the first dimension that MHA should consider should be batch first. But anyways, let's see now what happened. After training, okay, so clearly something is missing here. Okay, training loop is committed. Of course, that's right. Yeah, now it should be fine. Okay, this is post-training embedding. Looks like they are similar. Yes, after training, there is very good cosine similarity. And yeah, I just want to show this retrieval. That was my only purpose of running this. Orange circle. So now this is the first task. First task is for a given image, what is the perfect caption. Perfect caption, orange circle left. We know that this is orange circle left. So it is indeed the perfect caption. This is for this caption, which one is the best image. For orange circle top right caption, this is the best image. And if each time we run this, it picks a random image and it shows the, I don't know why both of them are square. I don't know why the shape remains the same. When I ran, yeah, see now it's different. See, image 18 best caption. So image 18, this image is, we know it's brown square left, and indeed that caption is picked up. And this is purple triangle top right is the input caption. Corresponding to that, the best image is this. So clearly our model is working very, very well. Yeah, so if the in the code which I shared with you, in case if I accidentally mask the training loop, please unmask it. I mean, this was accidentally commented out, but you see the validation score is coming down. I just want to run the 3D thing once more, just to ensure that for 3D also I can recover or not recover. So 3 dimensions and attention head is equal to 3. Let's see how bad is our fetching at the last. So validation loss is decreasing, and post-training, see the embeddings look very similar. Pre-training embeddings were looking like this, completely dissimilar for the 3 dimension. And when we are fetching the image, purple square right, yeah, there is mistake because this is 3D. In 3D embeddings, we can capture only so much information. We can't capture everything. We are expecting this three numbers to capture everything that is there in this image, this text and in this image, which is impossible. So clearly it's making mistake. But you can see by increasing the number of dimensions to even 12, I think this will work. You don't need 64. So see, now with just 12 dimensions, your validation is much better. These are now the 12 dimensions after alignment. And then at the end, gray square top, and this is gray square top, blue square right, blue square right. So you can play with this to see for just bare minimum dimension whether it works or not. Now let's do one last thing. We are about to wind up. One last thing. Why did we call this as a NanoVLM, right? So let's do a quick calculation about how many exact number of parameters are there. So image encoder had input as 32 by 32 by 3. It was 32 pixels by 32 pixels multiplied by 3 channels. And it was getting converted to 16 by 16 with 32 channels, which means I have a 3 by 3 kernel with 3 input channels and 32 output channels, then plus 32, right? So let me bring my calculator to see what this number is. So 3 times 3 times 3 times 32 equal to 864 plus 32 will be 896. So this has 896 parameters. Then the next one will be 32 channels at the input, 64 at the output, 3 by 3 filter plus the bias. Then this will be 32 times 3 times 3 times 64 plus 64 equal to 18496. Please do the calculation along with me. I hope I am not making mistake. 32 times, oh, is it? Okay, let me do once more. 32 times 3 times 3 times 64 equal to this 18432 plus 64. It's correct, right? Okay, I hope it's correct. If I'm making a mistake, we'll see at the end. Then next one is 64 in the input, 128 at the output, 3 by 3 filter plus 128 bias. So 64 times 3 times 3 times 128 plus 128, which is 73,856. Then next item is 128 at the input, 256 at the output, 3 by 3 filter. So 128 multiplied by 3 multiplied by 3 multiplied by 256 equal to this, oh no, 128 times 9 times 256 equal to, then with this we add 256. See, now the later layers are contributing so much. So 295,000, 295,168, 168 or 169, I forgot, 168, whatever. Then global average cooling has 0, doesn't contribute anything. Then this is the embedding 256 projection, 256 times 64 plus 64, which is 16448. And then last is 128. This is the normalization layer norm. So if you add all of this, you will get a number like this: 400,000, 4,000, 404,992, basically around 400K parameters. So around slightly less than 500,000. Then in text encoder, let's think about the parameters. I have vocabulary embedding. So I had an nn.embedding, which was 22 by 64. So this is 1408. Then I had position embedding. So I required for 4 positions, I need 64 dimensional vector. So this is 256. Then in multi-head attention, I have, let's say, 4 attention heads. We also had a linear projection layer in the code. So which linear projection in the convolution neural network? So linear or in multi-head attention. In CNN, this is itself is the linear projection. 256 times 64 plus 64. Now in text encoder, in MHA, we have weight matrix for query, weight for key, weight for value. So if I have 64 dimensional embedding and 4 heads, each in query space, key space, and value space, dimensionality will be 16, which means the WQ matrix will be 64 by 16, WK will be 64 by 16, WV will also be the same, and it will have bias. So 64 by 16 plus 16 for the bias. And I have query, key, and value. That's why I have this 3. And I have 4 attention heads. That's why I have 12480. But there is one more thing. At the output of multi-head attention, we are concatenating. And to mix those concatenated 64 dimensional embeddings, we have an output projection layer, which is part of the multi-head attention. So that projection will convert numbers from 64 dimensional concatenated outputs to 64 dimensional mixed outputs, so that it's not just 4 multi-head attention values simply concatenated, proper mixing is happening. So this happens through a 64 by 64 matrix with 64 bias numbers, bias values. So that will be 64 times 64 plus 64, which is 4160. And then you have a projection. The projection was the classification head like mode. Where is that? This one, this projection. So self dot projection was an nn dot linear from embedding dimension to embedding dimension. So that will also contribute 64 by 64 plus 64, because projection, the input dimension just happened to be 64, output has to be 64, and bias will also be 64. So this will also be 4160. Final layer normalization is you have 64 dimensions, beta and gamma for each dimension. So 128. If you add all of that, you will simply get 22,592. So total number of parameters is 4,992 plus 22,592. So this is what, roughly 4.26 or 426K or 0.426 million parameters. Let's call it as 0.45 million parameter for a rough figure. So this is why it's nano. Typically, models with less than 1 million parameters we can call as nano. So this is the reason why we are calling this as a nano vision language model. So I hope this is a good time to stop the lecture. The lecture has gone 1 hour extra than I expected, but I kind of expected in the back of my mind that it will go beyond time, but I hope it was worth your time and you enjoyed it. Please try coding once, at least the 3 parts yourself, the text encoder, image encoder, and clip loss. Other parts are okay. Other parts you can use my code directly, but just try with these 3 things. I think you will learn a lot from that process. Updated collab link I will share once in the chat. 1 second. Also, just play with the dimensions because for 3 dimensions, it's clearly not working. For 12 dimensions, it's working very nicely. Maybe for 6 dimensions also, it may work. The thing is, lower dimensions means you can plot and get a lot of meaningful insights from it. So just try this out. I hope you have enjoyed the lecture. You please read the papers. You can start with, even if you skip the BERT paper, I think it's fine. But at least read the VisualBERT paper and VLBERT. Those 2 papers might be really good for you. Few number of pages, and then I don't think it'll cause you a lot of mental struggle. I think it'll be fine. So thank you so much, everyone. We'll meet again next week. Hope you learned a lot, and hope you're enjoying the series. See you soon. Bye.